Marhaba. Okay. In this video, we will continue building up our arsenal of proof techniques. So previously, we learned how to tackle universal statements, how to prove conditional statement via a direct proof. So to prove alpha implies beta is true, we assume the hypothesis alpha to be true, and then we show beta must be true, beta the conclusion. We also learned an indirect proof to prove a conditional statement, alpha implies beta. We can prove it by proving its contraposition. We can prove it by showing not beta implies not alpha. Okay, today we want to learn a new technique which we will add to our arsenal, and it's called a proof by contradiction. So let me explain the strategy of this technique. So let's say to prove a statement alpha is true, we do the following. First, we say, okay, suppose it is false. So suppose alpha is false. In other words, suppose that not alpha is true. So let me write it here. So suppose not alpha is true. Okay, and next we can use what we are allowed to use in proofs, which are the axioms, the rules of inference, a previously proved theorems, until we get a contradiction. So get a contradiction. This is our goal, to get a contradiction. And what is a contradiction? It's a statement which is always false. Recall that a contradiction is a statement which is always false. For example, it has one form of a contradiction is R and not R, where R is any statement. So if you get a statement and its negation, this means you got a contradiction. Okay, at this point, okay, you say there's something wrong because we used, we used axioms, and for axioms, we assume them to be true. We used rules of inference, and we checked that rules of inference are valid arguments. And the theorems should not cause any problems because we proved they are true by writing down a proof. So the only place where which allowed for getting a statement which is always false is the very first step, which is supposing alpha is false. So this assumption that alpha is false cannot happen. Okay, so alpha can't be false, but we know that alpha is a statement in logic. It's either true or false. We don't have any third option, but we know it can't be false. This tells us we're only left with one choice for alpha, which is to be true. So we conclude that alpha must be true. So let's sum up. To prove that a statement alpha is true, to prove alpha is true by contradiction, we assume it is false, and we get a contradiction, and we conclude that alpha must be true. Because assuming it is false leads to a contradiction, to a statement which is always false. Okay, so let's take a quick example. So example, prove that the cubic root of 345 is strictly bigger than 7. Okay, so we want to prove this. One way to do it is calculate using a calculator what is the cubic root of 347 and check if it's strictly bigger than 7. Well, another way to do it is proof by contradiction. We can prove this by contradiction. So this is our statement alpha that we want to prove by contradiction. So what is alpha? Alpha is the statement which say, if you want, alpha says the number cubic root of 345 is strictly bigger than the number 7. So we want to prove alpha is true by, let's use proof by contradiction. So assume it is false. So suppose alpha is false, which means suppose that the cubic root of 347 is not strictly bigger than 7. This means that the cubic root of 345 is less than or equal to 7. Okay, so suppose this. Now we can take the cube of both sides. So take the cube of both sides of the inequality to get what? To get that 345 is less than or equal to 7 cubed, which leads to 345 is less than or equal 7 cubed is 343, and clearly this is a contradiction. Okay, this is a statement which is always false. Like 345 is not less than or equal to 343, so which is a contradiction. Okay, this means that this assumption can't happen. This is false, and this means that the cubic root of 345 is not less than or equal to 7. It is what we want. It is strictly bigger than 7. Okay, so this is an easy application of a proof by contradiction to prove that the cubic root of 345 is strictly bigger than 7. Okay, so this statement leads to a contradiction, so this statement is false. And its negation is true. This is the negation, and this is the true statement. Okay. You can check, you compute the cubic root of 345 and see that it's strictly bigger than 7. Okay, now let's use proof by contradiction to prove another famous fact in mathematics, which says that the square root of 2 is an irrational number. So let me first prove let me first define what we mean by irrational numbers. So definition. So now our domain will be the set of all real numbers. So real numbers. Say this is the real number line, and you can imagine real numbers as points on this number line. Okay. Okay. Now, if you choose any real number R, say, so choose R. Let's define this some terms. So definition. So a real number R is called rational if it is equal to an integer over an integer, where the denominator is not 0. Okay. So is rational, so it's called rational if there exist integers m and n such that R is equal to m over n and the denominator n is not 0. Okay, so let's say it again. We call a real number rational if it can be expressed as in the form of m over n, where m and n are integers and n is not 0. Okay, so in this case we call R a rational number. Okay, let's take examples of rational numbers. For example, 4 is a rational number because it can be expressed as 4 over 1, or say 12 over 3, where 12 and 3 are both integers and the denominator 3 is not 0. Here 4 over 1 are both integers and the denominator is not 0. So 0 is a rational number because it can be expressed as 0 over 1. Well, any integer n is rational. Choose any integer, say 7, then 7 can be written as 7 over 1, and both 7 and 1 are integers. Okay, now half 0.5 is a rational number because it can be expressed, say, as 1 over 2, or 4 over 8, or 10 over 20. Okay, so there are many ways, and see, all of these are an integer over an integer where the denominator is not 0. See that to show that a number is rational, we need to go to the world of integers. So notice R is a real number. So R is from the world of real numbers. To show that it is a rational number, we go to the world of we need to go to the world of integers and find an integer m and integer n such that m over n is R, and n is not 0. And see, the integers live inside the real numbers. Okay, now what does it mean for a real number to be not rational? So this is called irrational. So a real number R is called irrational if R is not rational. So what does it mean to be not rational? It means we cannot find integers m and n where n is not 0 and m over n is R. So it means when we go to the world of integers, no matter how hard we search for m and n, we can't find them such that m over n is R. This is in the case of irrational numbers. Okay, so if we know that a number is irrational, it means that it's impossible to find integers m and n where m over n is R and n is not 0, and n is not 0. Okay. So now what we want to do is we want to prove that the number square root of 2 is an irrational number. But before we start proving, I want just recall we proved before a corollary. So it was an easy. We proved in the video about direct proofs that if n is odd, then n squared is odd. And we wrote down a corollary of this theorem. It's contrapositive, which says if an integer n, if n is an, if, sorry, the contrapositive says if n squared is an even integer, then n is even. And just a second. We said, I want to write it in the correct way, let n be an integer if the square of n is even, then n itself is even. Okay, we will use this today. This was an easy consequence of the theorem which says if n is odd, then n squared is odd. Its contrapositive says if n squared is even, then n is even. Okay, so let's prove our theorem of today. The main theorem of today says that the number square root of 2 is an irrational number. So the number, the real number square root of 2 is irrational. Okay, so this statement is the statement alpha that we want to prove by contradiction. Okay, so think of this as alpha. We want to prove it by contradiction. So suppose alpha is false and get a contradiction. This means alpha is true. Okay, let me say one more comment about rational numbers. Look here that if you have this rational number 10 over 20, we know that the 10 and 20, they don't have common, they have common divisors other than 1. For example, we can divide 10 and 20 by 5, or we can divide them by 2. So anyway, we can keep dividing. Okay, so look here, we can keep dividing the 10, say, let's divide it by 5, we get 2, and divide this by 5, we get 4, and now divide 2, still we have common divisors between 2 and 4, so we divide 2 by 1, 2 by 2 to get 1, and 4 by 2 to get 2. Okay, so this 1 over 2, we can stop here because 1 and 2, they don't have any common divisors but 1. Okay, so I just want to say that any rational number can be written in lowest terms. And by lowest terms, we mean where the numerator and the denominator have no common divisors but 1. Okay, so let's start proving our main theorem. Okay, so proof. We want to prove that square root of 2 is an irrational number. Okay, what is square root of 2? It's a real number with the property that when we square it, we get 2. So it is like some real number here. This is, say, square root of 2, and it has the property that when you square it, like when you multiply square root of 2 by square root of 2, you get 2. Okay, this is the property of square root of 2. Now we want to prove that this number is irrational. That is, it can't be written in the form of an integer over an integer. Okay, so we will prove this by contradiction. We start our proof by saying, for the sake of contradiction, suppose our statement alpha is false, so that the square root of 2 is not irrational, which means square root of 2 is rational. So suppose square root of 2 is rational. Okay, now, and we want to get a contradiction. What does it mean for square root of 2 to be rational? So by definition of rational, there are integers m and n such that where n is not 0, and such that square root of 2 is equal to the ratio m over n. Okay. Furthermore, we may assume that m and n have no common divisors, like positive common divisors, but 1. Or if you want, let me restate this. We can assume that this ratio m over n is in lowest terms, because if it's not, like if m and n have common divisors, we can divide m and n by common. We can say, let me explain it here. Say square root of 2 is rational. So say there are integers m over n. Say they have common divisors, so we can divide by this common divisor. So say we get m1 over n1. Say we still have common divisors between m1 and n1. We keep dividing. Okay, and 2, we keep dividing until we stop, say, at some L step, so ml over nl, and these, they only have 1 as a positive common divisor. Okay, so we can assume that m and n have 1 as the only common divisor. Okay. So here we know this, that m and n have have 1 as the only common divisor. Okay. Now what we will do, so again, we want to prove this statement by contradiction. We assume it is false. So assume square root of 2 is rational. Once we assume square root of 2 is rational, we get the following. We get that there are two integers, m and n, such that m over n is square root of 2, and m and n have 1 as the only common divisor. Okay, so all of this is all of these are consequences of assuming that the square root of 2 is rational. Okay, now we know as square root of 2 is equal to m over n by squaring both sides. By squaring both sides, we get what? We get square root of 2 squared. So square root of 2 squared is equal to m over n squared, which gives us square root of 2 squared is by definition is 2, because square root of 2 is the number which when you square you get 2, and this is equal to m squared over n squared. Now if we multiply both sides by n squared, we get that 2 times n squared is equal to m squared. Okay, so look, what was n? Okay, m and n are integers. Now since m is an integer, then n squared is an integer, and this means that m squared is equal to 2 times some integer. This means that m squared is an even number. Okay. So m squared is even. But we can now use a previous theorem. We know that if the square of an integer is even, then the integer itself is even. Okay, so since m squared is even, we know that by a previous theorem, we know that m is even. Here we are using mod exponents. Like this is the hypothesis of this conditional statement. So remember, mod exponent says if a conditional statement is true and its hypothesis is true, you can conclude its conclusion. So we have this conditional statement, its hypothesis is true, that m squared is even, we can conclude that m is even. But we don't say in proofs we are using mod exponents. Okay, so here m is even, we know m is even. What does it mean that m is even? So m is equal to 2k for some integer k. Okay, this is by definition of even. Since we know m is even, this means that m is the twice of some integer. Now let's substitute m is equal to 2k in this equation. So now we get that, okay, 2n squared is equal to m squared, but m is 2k all squared. Okay. If this is true, then this arrow says implies. Okay, this implies that 2n squared is equal to 4k squared. Now we can divide both sides by 2, and this implies that n squared is equal to 2k squared. Okay, now look at this. K was chosen to be an integer, and k squared is an integer. And so n squared is twice an integer. This means that n squared is even. Okay? So we can conclude, that n is even. Again, by using the previous corollary, that if n squared is even, then n is even. Okay, so here, since n, so from here, we know that this means that n squared is even. And now using the corollary, we know that if n squared is even, we conclude that n itself must be even. And now we have a contradiction. Why? Because here we have that m is even, and here we have that n is also even. Since both m and n are even, this means that, so 2 is a common divisor of m and n. Okay, so let me highlight this statement. Okay, now look at this statement. Let me put it in a red box. So this says, okay, now we assumed square root of 2 is rational. We deduce two statements. One statement says m and n have 1 as the only common divisor. Let's call this statement R, say. And the other statement, we also deduced another statement, which is the negation of R, that 1 is not the only common divisor, 2 is also a common divisor. So this is not R. This means we have a contradiction. R and not R is a statement which is always false. Okay? We got a contradiction as we derived two statements. One says that m and n are integers with 1 as the only common divisor, and m and n have 2 as a common divisor. So this is a contradiction. These two statements, R and not R, were consequences of our original assumption that square root of 2 is rational. So this can't be the case. So square root of 2 can't be rational, because if it is, we get a contradiction. This means that square root of 2 must be an irrational number. Okay, so we got a contradiction. Therefore, square root of 2 is not rational, can't be rational, is an irrational number. And the proof is done. So let me just revise quickly. What is the proof? The structure of the proof. We want to prove that square root of 2 is an irrational number. We will prove this by contradiction. So we say, suppose the statement that we want to prove is false. So in other words, suppose square root of 2 is rational. We deduced from this assumption two contradictory statements. One says there are two integers, m and n, which don't have a common divisor, but divisors but 1, and another statement which says that 2 is a common divisor of m and n. This is a contradiction, and so our assumption can't be true. So square root of 2 is an irrational number. It is not rational. Okay. So this is a very nice application of showing that the square root of 2 is an irrational number. Okay, let me also give you another quick application of proof by contradiction to prove conditional statements. So let's prove, how to prove. We want to use proof by contradiction to prove conditional statements. So to prove a conditional statement P implies Q. How will we use proof by contradiction? So first we start as we are starting a direct proof. So assume the hypothesis is true. So assume P is true. Now remember, what do we want to show now? We want to show that Q is true as well. We assume the hypothesis, we want to show the conclusion. Okay, so for this, to show that Q is true, we will show it by contradiction. So show Q is true, the conclusion Q is true by contradiction. So how will we show Q is true by contradiction? This means suppose Q is false. So suppose Q is false. And then use whatever you can use, what you are allowed to use. So use axioms, use rules of inference, you use previous theorems, and you also use our original hypothesis that P is true. So use P, use the hypothesis P. Okay, the hypothesis of the conditional statement that we want to prove. Okay, use P to get a contradiction. Get a contradiction. Once we get a contradiction, this means that our assumption that Q is false is not correct. So Q must be true. Now conclude that Q must be true. Okay, so what happened here? We assumed P is true, and we concluded that the conclusion Q must be true. So therefore, the conditional statement P implies Q is true. Okay, so this is how we can use proof by contradiction to prove a conditional statement. Okay, again, to prove P implies Q is true, we assume the hypothesis P is true, and we show the conclusion Q is true by contradiction. So we assume Q is false, we get a contradiction, and conclude that Q must be true. So overall, we assumed P to be true and concluded that Q must be true. This shows that the implication, the conditional statement, P implies Q must be true. Okay, so let's have a quick example on applying this strategy. Okay, so theorem, let's prove the following theorem. Okay, let n be an integer. Prove that if 5 times n is odd, then n itself is odd. Then n is odd. So proof. Okay, now, so let's look at the logical form structure of the statement. It says for every integer n, if 5n is odd, then n is odd. Okay, so this is a universal quantifier for every n in the domain of integers. Now, this is a conditional statement, if then. This is P, the hypothesis, and this is Q, the conclusion. Okay, so let's start by taking care of the universal quantifier. So choose any arbitrary integer n. Okay, now we want to prove the conditional statement with the use of proof by contradiction. So we start by assuming the hypothesis to be true. So assume P is true. Assume that 5n is odd. Okay, so we chose an integer n, and we assume 5n is odd. Now we want to show that Q, the conclusion, is true. So we want to show n is odd. But we will show this by contradiction. So we say here, for the contrary, suppose Q is false, which means suppose that n is not odd, that n is even. And now we need to get a contradiction. Okay, so what does it mean n is even? So there exists an integer k such that, so st such that n is equal to twice k. Now we want to get a contradiction. Okay, one statement we have which we can contradict is this one, that 5n is odd. So we assumed that 5n is odd. This is P. So here we can use P, the hypothesis. Okay, so this is 5n is odd. This is the hypothesis. Okay, so let's see now what we know about 5n when we assumed n is even. Now 5n is equal to 5 times 2k. Okay, but by associativity and commutativity of multiplication, this is equal to 2 times 5k. But since k is an integer, then 5k is an integer. Let's call 5k, say, L. So this means that 5n is equal to 2 times L, 2 times an integer. So L is an integer here. Since 5n is 2 times an integer, this means that 5n is even. But this contradicts that 5n is odd. So here we have 5n is odd. We assume this to be true. And here 5n is even. So like this is R and this is not R. R and not R is a contradiction. So we have a contradiction. We got a contradiction. And this means that assuming the conclusion to be false is not the case. So so supposing that n is even led to a contradiction. So let me do it in blue. Supposing n is even gave us a contradiction. So n can't be even, n must be odd. So n must be odd. So look what we did. We assumed that 5n is odd, and we concluded that n is odd. This means we proved that if 5n is odd, then n is odd. So the proof is complete, and the proof is complete. See how the structure of the proof, it's written in complete English sentences with full stops and commas. And this is the structure again. We need to prove if n is an integer, then if 5n is odd, then n is odd. So we choose any integer n, and we assume the hypothesis that 5n is odd. And now we need to show n is odd by contradiction. So this is the statement that we want to prove to be true by contradiction. So assume it is false. So assume n is even. Once we assume n is even, we conclude that 5n is even. But we assumed in the very beginning that 5n is odd. This is a contradiction. And so our assumption that n is even can't be true. So n is odd. Okay. Overall, we assumed 5n is odd and concluded that n is odd. This means we proved the conditional statement. If 5n is odd, then n is odd. And this is the end of this video about proof by contradiction.